Hi, I'm Yoon from Carnegie Mellon University. Today, I will introduce our paper, EiGLasso, Scalable Estimation of Cartesian Products of Sparse Inverse Covariance Matrices. Let's consider a general problem of learning dependencies in multivariate data. Assume that we are given gene expression data for multiple samples and genes. Standard Gaussian graphical models assume IID samples and learn the feature dependencies only, in this case, the gene network. Quick, which used the second-order method, is the state-of-the-art Gaussian graphical models. There have been several works that try to learn both sample and feature dependencies. The idea is that by jointly learning two graphs, the model can use more information from the interaction, and we can expect a better graph recovery than learning each graph independently. We can represent the joint graph as a Kronecker-sum or Kronecker-product of two inverse covariances. As you can see in the figure, Kronecker-sum has a sparser and intuitively more appealing structure than Kronecker-product. Despite this desirable structure, Kronecker-sum models were slower than the ones using Kronecker-product. The state-of-the-art for Kronecker-sum, EiGLasso, uses first-order method and scales only to a few hundred samples and features. While EiGLasso used first-order method and had limited scalability, EiGLasso adapts the second-order method in quick and is orders of magnitude faster than EiGLasso. We also suggest a clearer way to work with the non-identifiable parameters, which is an intrinsic issue of Kronecker-sum. While EiGLasso uses reparametrization and identifies the parameters every iteration, EiGLasso works with the original Kronecker-sum parametrization and identifies the parameters only once at the last iteration. The first key contribution of EiGLasso is the adaptation of the second-order method in quick. This is non-trivial because naive adaptation results in gigantic gradient and Hessian that are expensive to store and compute. In quick, the size of gradient and Hessian depends only on the feature dimension, whereas in Kronecker-sum model like EiGLasso, because of the inflated Kronecker-sum matrix, the size of gradient and Hessian depends on the product of sample and feature dimensions. The key idea behind EiGLasso is that we collapse the inflated structure of Kronecker-sum and compute the gradient and Hessian efficiently through eigendecomposition. Let data and psi be the two matrices, each for feature and sample dependencies. Then we can see that the Kronecker-sum has a sparse structure. If we naively adapt second-order method, we need the inverse of the Kronecker-sum that appears in both gradient and Hessian. However, we exploit the sparse structure of Kronecker-sum and collapse this gigantic inverse matrix into the gradient for theta and psi. In addition, we prove in our paper that it is possible to compute the gradient without explicitly computing the gigantic inverse. To briefly introduce how it works, the gradients have the same set of eigenvectors as the two smaller feature-wise and sample-wise graphs. Eigenvalues of the gradient have a form of the inverse of sum of eigenvalues from each graph. While non-computation of gradient has p cube, q cube complexity, our approach has p cube plus q cube, which is a significant save. We can use a similar approach to Hessian. Hessian is given as a Kronecker product of summand in the gradient computation, which means Hessian uses the same set of eigenvectors and eigenvalues. Although this is much more efficient than naive computation, it is still expensive to store and compute the entire Hessian. So we suggest a spectral approximation of Hessian by using only k smallest eigenvalues from the other graph, in this case psi. According to our experiments, only a single eigenvalue from the other graph, k equals 1, suffices to converge to the same optimum, and also has a much lower complexity. The second key contribution in EiGLasso is that the optimization is not affected by the non-identifiable parameters of Kronecker-sum. As we can see, the Kronecker-sum of two matrices has the same value even if we subtract or add the same diagonal matrices from each. However, we prove in our paper that this non-identifiability does not affect the gradient and the Hessians and the optimization. Because of this, we need to identify the parameters once after convergence. Our experiments show that EiGLasso is orders of magnitude faster than EiGLasso. We can see that EiGLasso is faster than EiGLasso with all degrees of Hessian approximation, and Hessian approximation with only one eigenvalue suffices to converge to the same optimum with much fewer iterations than EiGLasso. On 1,000 by 1,000 graphs, EiGLasso did not converge within 24 hours, whereas EiGLasso took a few hundred seconds. As we can see, EiGLasso also has better precision recall with all degrees of Hessian approximation, which looks almost identical here. This higher accuracy can be directly seen in the plot of the estimated inverse covariances. In conclusion, EiGLasso uses second-order method to learn Kronecker-sum of graphs, and it is orders of magnitude faster than the state-of-the-art, and also EiGLasso uses a simpler approach to non-identifiable parameters of Kronecker-sum. The future works include big extension to lift memory constraint, and also the convergence analysis to prove that EiGLasso has quadratic convergence rate. Thank you for listening.